Welcome to this deep dive. Today we're looking into the Jackknife and Bootstrap methods in statistical estimation.
Yes, these are really powerful tools, especially relevant, I think, for professionals in ML, data science, technology, anyone dealing with model reliability.
Absolutely. They're resampling techniques, right? Offering alternatives to maybe more traditional parametric approaches when you need to assess uncertainty.
Exactly. And our focus today is pulling from that seminal 1977 Rietz Lecture by B. Efron. It's titled Bootstrap Methods. Another look at the Jackknife.
A classic paper. So our mission really is to unpack the key research ideas, the practical methods, and, the main takeaways from Efron's work on these two techniques.
And understanding them gives you, the listener, really valuable tools. Think assessing estimated variability, bias.
Constructing confidence intervals, too, all crucial stuff for robust model development and evaluation.
Definitely. So perhaps we should start with a quick overview of both.
Good idea. Let's start with the Jackknife. It came first, didn't it?
It did. Introduced earlier than the Bootstrap, it's a non-parametric method, mainly used for estimating the bias and variance of some statistic you're interested in.
And its core idea is that delete one approach.
That's right. You systematically remove one observation at a time from your data set and see how the statistic changes.
Okay, and then the Bootstrap.
The Bootstrap came later. It's generally seen as, well, more widely applicable, a more dependable resampling method overall.
Why is that?
It's particularly good at approximating the sampling distribution of a statistic, even in really complex situations where the Jackknife might struggle a bit, or where parametric assumptions just don't hold water.
Right. And Efron's paper aimed to connect the two.
Precisely. The paper explains the Jackknife, but sort of in light of the Bootstrap. It presents the Bootstrap as essentially a linear expansion method.
Okay.
And it argues the Bootstrap often performs just as well, or sometimes even better, than the Jackknife, especially when you're dealing with nonlinear problems.
Interesting. Okay, let's maybe dig into the Jackknife details first then. How does that delete one thing actually work?
All right, so imagine you have your random sample, let's call it X. It's got n observations, X out up to X be I20 by 820 by 99.
Okay.
The Jackknife procedure calculates in different estimates of whatever statistic you care about.
One for each observation you leave out.
Exactly. You create n sub-datasets. Each one is the original dataset minus one specific observation. Then you calculate your statistic on each of those n one-size datasets.
Got it. So you end up with slightly different values for your statistic, the leave one out estimates.
Yep. And then you use those to compute the final Jackknife estimator for your parameter. Let's call it n.
F. How's that calculated? Is there a formula?
There is. The Jackknife estimate, let's call it RxF, is n times minus n nines 1 times F.
Whoa, okay, break that down. What's n and 9?
Right, so n is just your standard estimate calculated using the full original sample, all n data points.
Okay, the estimate you'd normally calculate.
Yes, and so simply the average, the mean, of all those leave one out estimates you just calculated.
Ah, I see. So the formula basically takes your original estimate and then adjusts it based on the average of the estimates you got when leaving points out.
Exactly. It's kind of a bias correction in a sense. It looks at how much influence each individual point has.
Clever. What about that t-distribution thing mentioned in the paper? Tukey's idea.
Ah, yes. Tukey originally suggested that you could treat the Jackknife estimates, or rather a statistic derived from them, as if they followed a t-distribution with n1 degrees of freedom.
And why would you do that?
Well, the main motivation was to construct approximate confidence intervals for your parameter f based on the Jackknife results.
But it's just an approximation.
Yes, very much an approximation. Its accuracy can, vary quite a bit depending on the data, the statistic. It's not always reliable.
Okay, so that's the Jackknife, deterministic, delete one. Now, the Bootstrap, you said it's different.
Very different in its core mechanism. The one-sample Bootstrap procedure starts by creating something called an empirical probability distribution.
Empirical distribution.
From the data itself.
Exactly. You basically treat your sample as the entire population. You put a probability mass of 1n on each observed data point you have.
So each of my n data points has an equal chance, 1n, of being picked.
Precisely. F is just a discrete distribution based entirely on your observed sample.
Okay, so you've got this F. What next?
This is the key step. You draw a new random sample, also of size n, but you draw it with replacement from this empirical distribution F.
With replacement. Okay, so a single data point from my original sample could show up multiple times in this new sample.
Absolutely. Or it might not show up at all. That's the core difference from the Jackknife. This new sample is called a bootstrap sample. Let's call it X.
XX here. XA array XD by E 20 by 820 by 99. So it has the same size n, but it's made up of points drawn randomly with replacement from the original set. Correct. And this sampling with replacement introduces that crucial randomness that allows the bootstrap to work.
So once I have one bootstrap sample, X, what do I do with it?
You calculate your statistic of interest, say R, on this bootstrap sample. So you get RxS.
Okay.
Now, you don't just do this once. You repeat this whole process many, many times. Generate lots of independent bootstrap samples, X0, XX, and so on, and calculate the statistic for each one.
Ah, okay. So you end up with a whole collection of RxS values.
Exactly. And the fundamental idea, the magic of the bootstrap, is that the distribution of these RxS values approximates the actual sampling distribution of your original statistic, RxF.
So by repeatedly resampling from my data, I build up a picture of how my statistic would behave if I could draw many samples from the true underlying population.
That's the intuition, yes. It's a simulation-based approach to understanding the variability and distribution of your statistic.
How many times do you typically need to repeat this?
Well, theoretically, you could figure out the exact bootstrap distribution by considering all possible bootstrap samples. But the number of possibilities grows incredibly fast, so that's usually computationally impossible.
Right.
So in practice, we use a Monte Carlo approximation. You generate a large number of bootstrap samples, maybe thousands, maybe tens of thousands, calculate the statistic for each, and the distribution of those calculated statistics serves as your approximation.
So it's simulation heavy?
It can be, yes.
Yeah.
Though the paper also mentions alternative approaches like using Taylor series expansions to approximate the bootstrap distribution, especially if you're focused just on things like variance or bias. But the Monte Carlo method is the most common.
Okay, that clarifies the mechanics. The paper uses estimating the median as an example for the bootstrap.
Yes, it's a nice concrete example. So say you want to estimate the median of some underlying distribution F based on your sample.
How does the bootstrap help?
You'd follow the procedure we just discussed. Create F, then draw many bootstrap samples X with replacement. For each X, you calculate its median. Let's call that theirs.
So you get a distribution of bootstrap medians, their values.
Exactly. And by looking at the spread and shape of this distribution of F values, you can estimate the standard error of your original median estimate, construct confidence intervals for the true median, and so on.
Does the paper give specifics?
Yeah, it details a case with N13 observations, where the true median is assumed to be the seventh ordered value, M7. It actually calculates the exact probability distribution for the bootstrap median in this specific small example.
Showing how likely different values are for the bootstrap median.
Precisely. It shows the probabilities for different counts of bootstrap observations falling below the true median. It's a way to illustrate exactly how the bootstrap distribution is formed.
And it also mentions squared error.
Yes. It discusses calculating the estimated squared error of the bootstrap median and talks about its asymptotic properties, basically, how its accuracy behaves as your original sample size n gets larger.
Which is reassuring, knowing it gets better with more data.
Generally, yes. That's a key theoretical underpinning.
Okay. Another application mentioned is error rate estimation in discriminant analysis. That sounds very relevant for machine learning folks.
Absolutely. This is a common problem. Say you have two populations, F and G, and you collect samples from each X from F, Y from G. You build a classifier, maybe a linear discriminant rule, to assign new observations to either F or G.
And the question is, how well does this rule actually perform? What's its error rate?
Right. The naive approach is the apparent error rate. Just see how well your rule classifies the data you trained it on. But that's usually overly optimistic.
Because it's tested on the same data it learned from.
Exactly. So how can Bootstrap help get a better estimate?
How does it work here?
You create Bootstrap samples from both your original samples, X and Y. You get a Bootstrap X and a Bootstrap Y. You then train your discriminant rule on this combined Bootstrap data, X, Y.
Okay, so you're simulating the training process on resampled data.
Yes. Then, to estimate the error rate for, say, population F, error F, you take the original Bootstrap samples drawn from F, the components of X, and see what proportion of them are misclassified by the rule you just trained on the combined XY Bootstrap data.
Ah, so you train on a Bootstrap set and test on the relevant part of that same Bootstrap set. You repeat this many times.
You repeat the whole process many times. Generate XY, train the rule, calculate the error rate, error F, and similarly for G. Then you average these error rates across all your Bootstrap repetitions.
I see. So this gives a potentially more realistic estimate of generalization error.
That's the idea. Table 2 in the paper shows results comparing this Bootstrap estimate with the apparent error rate and also cross-validation for sample sizes of 10 and 20 from each group.
And what do they find?
The key finding was that the Bootstrap estimate was generally less biased, closer to the likely true error rate than the often very optimistic apparent error rate. It performed comparably to cross-validation in their examples.
That's a really practical benefit for model evaluation in ML. Less biased error estimates are crucial.
Definitely. It helps avoid fooling yourself about model performance.
Now, the paper's title, Bootstrap Methods, another look at the Jackknife, obviously implies a deep connection. You mentioned the Bootstrap helps understand the Jackknife.
Yes. Efron's argument is that the Bootstrap provides a kind of broader theoretical framework, and within that framework, the Jackknife emerges as a specific approximation.
An approximation? How so?
It can be shown that the Jackknife estimate, particularly for things like variance, is essentially a first-order approximation to the corresponding Bootstrap estimate.
First order, like the first term in a Taylor series.
Exactly that kind of idea.
Yeah.
Think of the Bootstrap as implicitly capturing more terms in an expansion that describes the statistic's behavior. The Jackknife mainly captures the linear or first-order part of that expansion.
So the Bootstrap might be more accurate, especially if the statistic's behavior isn't linear.
Precisely. The paper uses a Taylor series expansion of a Bootstrap replicate, RAP, around the original estimate, RAP, and shows how the Jackknife variance estimate relates directly to the linear terms in that expansion.
Which explains why the Bootstrap often performs as well or better, particularly for complex, nonlinear statistics where those higher-order terms matter more.
That's the connection Efron draws. The Jackknife is computationally simpler, often faster, but the Bootstrap is, in a sense, statistically more complete.
So Jackknife as a useful, perhaps quicker approximation, while Bootstrap is the more general, often more accurate approach.
A good way to summarize it.
The outline also briefly mentioned Wilcoxon's statistic and regression models. What's the point there? Just showing breadth.
Pretty much, yes. Including Wilcoxon's statistic, which is used for comparing two independent samples non-parametrically, just illustrates that Bootstrap isn't limited to simple things like means or medians.
It can handle more complex statistics.
Right. It shows the method's versatility. You can apply the Bootstrap resampling idea to approximate the sampling distribution of even quite complicated non-standard statistics where analytical formulas might be intractable.
And regression models.
Similarly, mentioning regression highlights that you can bootstrap residuals or pairs in a regression context to estimate the distribution of your regression coefficients, the betas.
Which gives you confidence intervals or standard errors for those coefficients without necessarily assuming normally distributed errors.
Exactly. It provides a way to assess the uncertainty in your model parameters under weaker assumptions. Again, demonstrating the broad applicability of the resampling principle.
Okay, we've definitely covered a lot of ground. Let's try to summarize the main takeaways from this deep dive into Efron's paper.
Sure. So I think the key points are both Jackknife and Bootstrap are really valuable resampling techniques. They let you assess estimator properties like bias and variance without needing strong assumptions about the underlying data distribution, which is often unrealistic.
Non-parametric powerhouses, essentially.
You could say that. The Bootstrap, sampling with replacement, tends to be more robust and more generally applicable, especially when things get complex or nonlinear.
While the Jackknife, the delete one method, is often simpler computationally and can be seen as a solid first-order approximation to the Bootstrap.
Exactly. It's often a good starting point, but the Bootstrap usually offers a more refined analysis.
And for our listeners in machine learning, data science, tech, why is really understanding these methods so important?
Because evaluating uncertainty is fundamental. These methods provide practical tools to quantify how much variability there is in your estimates, how biased they might be.
Which is crucial for building reliable models, right? And for making sound decisions based on data analysis. You need to know how much you can trust your results.
Precisely. It's about moving beyond just point estimates and understanding the uncertainty landscape. This leads to more robust systems, more credible findings.
So maybe a final thought for people to consider as they work with their own data and models.
Well, think about situations where you don't have massive amounts of data, or where you're building really complex models, maybe deep learning or intricate simulations. Traditional statistical methods might struggle there.
Because assumptions are violated or formulas are just too hard to derive.
Exactly. And in those challenging real-world spots, resampling techniques like the Bootstrap and sometimes the Jackknife can be incredibly powerful. They offer a computational way to get reliable statistical inference where theory alone might fall short. It pushes the boundary of what we can reliably analyze.
A crucial toolset for modern data challenges. Thank you for joining us on this deep dive.